We now move on to an exciting talk by this year's invited speaker for Research Scholars Day. I invite Dr. K.P. Krishnaraj to introduce Professor Raj Chhabra.
So again, I thank Professor Rajनीश for his quite insightful talk. I mean, I understand it involves a lot of economics to do carbon dioxide capture as well. So now this is an interesting, exciting talk which I have been looking forward to. I mean, and also I think it will be of use to the much use to the research scholars as well. So we have now Professor Raj Chhabra, who was our very own faculty, and he retired quite recently. Professor Raj Chhabra earned his BS, MS, and PhD degrees all in chemical engineering in the University of Roorkee, that is his BS, and Indian Institute of Science for his MS in 1976, and Monash University, Melbourne, Australia, 1980, where he got his PhD. And following a postdoc with the late Professor J.F. Richardson at the University of Swansea, UK, in 1984, he joined as an assistant professor in the Department of Chemical Engineering at IIT Kanpur. Currently, he is a professor in chemical engineering at Shiv University of Eminence, Shiv University, in the Department of Chemical Engineering. And his research interests are in the area of multiplayer systems. And I personally have read many of his books, particularly when I was teaching this transport phenomena last semester. I used his books for teaching non-Newtonian fluids. And his research interests are in primarily non-Newtonian fluid, which involve multiplayer force. Okay. And he is widely known chemical engineer with many recognitions. He is a fellow of all academies in India and has been a JC Bose Fellow from 2015 to 2020. He has more than 300 journal publications to his credit. And as I said before, he has co-authored many books. The exact number is 7. Now I invite Professor Raj Chhabra for his talk.
Okay, good morning. It's really a very special moment, like coming home. So many known faces here, old colleagues. Some of them are here unwillingly, some are here willingly. Some are here against their wishes to suffer it out. But I'm really very happy to see large number of students because they have no historical baggage, so they don't know what I'm going to say. Next, I'm really grateful to Professor Jayant Singh, Professor Kishan Raj, and whatever committee was. They must have seen something in me that maybe this guy deserves a chance to come back. So thank you very much for that. And thirdly, I am grateful to Professor S.K. Gupta for really getting me onto this business, which I'm going to talk about today. As a bit of a history, there was a course instituted exactly 25 years ago. It was called Introduction to the Profession, not Introduction to Chemical Engineering. And each department was supposed to teach on its own, whichever way they saw it appropriate. So students may not know, but our department has a very healthy practice. Faculty has a choice to say what he would like to teach, what he would not like to teach. And of course, if there are courses which nobody wants to teach, then it's head's job to teach himself. So this is how I ended up teaching this course. Secondly, on this idea, Professor Gupta had 100% attendance, which I don't think any student could match the 3 years I taught. And he was there on time, before time. We talked about it before the class, after the class, every time. So this is probably 90% belongs to him, but only 10% to me. So thank you, Santosh. Okay, so let's get to the crux of the matter, that I'm sure all of you are thinking that what I'm going to say. And this talk is exactly about that how do you think about things? So a very vague outline, I may not stick to it. Okay, so whenever I ask students that what is research, they say it's a very creative process. Then I ask them what is creativity, they tell me some definition. Then somebody says it's a activity which requires a scholarship. Then I asked them, what is a scholarship? So I thought to save that embarrassment, I just looked up dictionaries and I found the definition of a research, the careful study that is done to find new and report knowledge about something. I'm not so much interested in that, but I'm interested in research as a process. It doesn't really matter what problem you solve, how lousy your answer is, how lousy your solution is, but the question is the process you have gone through. And if you cultivate that process, then you can solve any problems, whether it's how to find the best match for you, how to find the best job. So I just want to move on and leave it here that all three are connected, but yet they're not very easy to define. They're very nebulous in that sense. Okay, so if we are not able to define something, you can ask a questions, what are the consequences, what are the manifestations? So you can ask, what has science done for us? Maybe that will give us a clue. It's like, blind people, when they feel, if you ask them to describe an elephant, so different people touch different parts of the elephant and their description is very different. And then if we have sufficient large number of people feeling the elephant, maybe we can construct a whole that how elephant might look like. So you can ask a reverse question, what science has done for you? This is somewhat easier. Smart devices, the clothes you are wearing, shirts you are wearing, clock, watches you have, shoes you have, everything in this room is a consequence of scientific research. So you can describe all these images, the products we use in every day, the polio vaccine, food, no chlorofluorocarbons, no dumping, drains to bay, and all those things. Science affects us all every day of the year, shaping society. It improves life, quality of life, longevity, quality of food. There is no, we are trying to do that there should be no hunger, no poverty. Everybody should have potable water and all those things. Or you can think of all these vaccines, medications, everything, or all this. But what it is important is that all these images show an aspect of science, but a complete view of science is more than any particular instance. This is I want to tell you. All of us think when we are young graduate students that what I'm doing is the most important work in the world. Yes, it is true, because what you are doing, you're investing 4 or 5 years of your prime time. It is very important. But I also want you to look at that what everybody else is doing is just as important, if not more important. Okay? So, but there is, how do you know that this is a sparrow, the normal birds you see in the campus? It sings a song. If I ask you a question, is it coded in its DNA that it will always sing this song, or does it learn this song after it is born? How will you do this experiment? You take a sparrow, newly born sparrow, and let it grow with the crows. Will it sing its own song, or will it learn something which among the crows? That will answer your question. This is also science. This is also research. You should wonder, birds fly every day hundreds of miles, yet they come back to the same physical location where their nests are, where their eggs are, where their babies are. How do they navigate? They don't have a smartphone. They don't have a GPS. They don't have a Google map. That's also science. Or we all lay a trap to catch a rat at home. But he's also smart, doesn't get caught every time. He's able to get the food, but doesn't get caught every time. So obviously he knows optimization techniques. Even when we cross the road, we do a probability calculation that am I going to get run over by the lorry which is coming from my left, or I'm going to cross the road. So they also do this mental calculation. This is also science. So this is why science is a very, very complex topic. And I think I say that even people who are doing what we call a very ordinary job, like a tailor or a baker or something, they're also doing scientific work because they're experimenting every day. They are creative, they are creating new recipes and all those things. So the question was posed when that if you want to become a world-class tennis player, what do? You go and get an equipment, tennis racket, shoes, shorts, gloves, whatever you need. Then you find a coach and undergo apprenticeship. Then you have a chance. Still, there is no guarantee that you'll become a world-class tennis player like Ivan Lendl or Borg or whatever. So, how does one become a researcher? Simply, IIT Kanpur gives you an MTech admission or a PhD admission and you say, I am a researcher. Isn't it? If you want to become a school teacher, you undergo training, teacher's training. If you want to become a nurse, you go undergo nurse training. Then why there is no training required to become a researcher? Or conversely, we can ask the question that if you really want to be a successful researcher, what toolkit you should possess? What skill set you should have? That will help you. Still, there is no guarantee that you may become a successful researcher or you may not. But what is the toolkit it would require, or what is the skill set you should have? Okay, so I want to, so how do you know that a tailor needs a scissors, measuring tape and sewing machine? First we have to know what is the profession of tailor. What does he do? So you have to ask, how does science work? Then only we can answer what kit we require, what toolkit we require. So science is all about testing ideas. You have a hypothesis. Like I ask you a question, how do birds navigate? Or how does a sparrow learn its song? Or how does animal psychology work? So we have an objective. So we want to have an idea. And you know, as Rajneesh said, that every day people are only talking about monetization. So there should be some benefits and outcomes, some community analysis and feedback. Some people just do it for the exploration part. For example, what was done in this great institution by Maninder Karwal, presently the director, prime numbers, your everyday life doesn't depend upon prime numbers. You don't give a damn that why should I know about prime numbers, what they are, where do I need them? But it's pure passion also. It can be just passion that you want to crack a problem. You know, in old days, kings and royal families will throw challenges, intellectual challenges, and people will just get a kick out of it by cracking that problem. So this clearly you can see there are arrows going in all possible directions. So one thing is that research is very, very non-linear, back and forth and all those things. It's not a linear process. It's not something like that you join a BS program and you have a sequence of courses, you pass exams, pass quizzes, get grades, whatever. Research is very different. I mean, days and months go by, you don't see any results. But then suddenly there is a eureka moment and you just feel on the top of the world on that day. So it's a very, very non-linear, very interactive, back and forth. You go the blind alleys to see that they're really blind and all those things. So people ask, why do research? It connects to many endeavors. For example, if there were no research, we will still have those ugly looking black phones just lying as a landline. You will not have a smartphone. To be able to use that phone, the other side should have the same instrument. You should be at home, close to the instrument, then only you can use it. Now you can be anywhere in the world. You can connect, okay? So it connects to many human endeavors. It enhances students' learning experience. That's the main thing. I mean, that's our main occupation, to keep them excited, to keep them passionate about it. It creates new knowledge. It disseminates knowledge. And in this age, no matter where you are, you have access to the same information as people in New York or London or Paris. That's research, because there was no internet in our days, okay? It's a development work, as Professor Rajneesh Kumar pointed out, that we have to improve efficiency, sustainability, and all those things. It requires new approach, some improvements. It promotes creativity. This is very important. I mean, all of us are creative in our own ways. My creativity need not be the same as your creativity. But all of us are creative. Some of us are good at with our hands. Some of us good at thinking about things, very abstract things. It is, of course, a bit of a politics also. So vision of a company, university, nation, your rankings depend upon that. Your personal ranking depends upon that and all those things. It helps in writing. That's very important for students. If you have a train of thought, you can organize them logically. It helps you writing also. After all, many people have published just their diaries, Anne Frank's diary and all that, just record of everyday things. So it allows you to collect your thoughts, organize your thoughts, train your thoughts. It's simply fun. Yeah, some people just enjoy it. I mean, before the Industrial Revolution 200 years ago, everybody was doing science for the sake of fun. People were farmers, they were magistrates, they were judges, but they made profound mathematical discoveries. Okay? They were just doing it for that. It fosters professional and personal life also. You feel good about it. A problem which nobody has been able to crack for the last 100 years, like Fermat's theorem, but then you feel, wow, I got it. So you go down in the history also. So research is also vital to sustain a strong economy, as you saw in the previous talk in a very, very explicit manner, in a very eloquent, very powerful manner. So no matter what your political affiliations are, but I think Swachh Bharat, 30 trillion economy, Atmanirbhar Bharat, they all are banking on young people like you. Modi will not be able to find a solution. You have to find the solution. Okay? I mean, so I think that's also a driver, main driver, that why so much money is being pumped, so much infrastructure is being created, all that. But anyway, so research does have a serendipitous aspect also. It happens at most unlikely moments. I'm not looking for anything that I find. So although many people probably will not think of Picasso as a very nice person, but leaving aside his personal life, I think he was a very, very creative person. So what it means is that if I know the answer to a problem, why would I spend my energy on that? I'm looking for something new to which I don't know the answer. That's what research is all about. Similarly, but your ability to spot patterns in a random event is an acquired trait. This is what you do in colleges and IITs and schools, Wikipedia and internet. It sharpens your ability to look for patterns where there may be very few or very difficult. Similarly, Louis Pasteur, in the field of observation, chance favors only the prepared mind, and that trait is sharpened by rigorous academics and by practical experience. So what that means is that, I think the best example I can give you is that all institutions have produced over toppers, 10 rankers, CGPA 10 gold medalist. Yet they settle down to a very, very low, comfortable physical life. They never challenge themselves. So if you have a skill set, if you have a ability, you have a potential, you should exploit it. This is what it is. Rigorous academics and practical experience, that every experience counts. Every negative experience counts even more than the positive experience. So research is also a complicated notion, and this is how students describe it. I have asked during my travels to the students in a very, very different stages, starting, middle, finishing. Some think it's a maze. There is no obvious start, no obvious end, where to start, where to end, because it's not a linear process. You cannot say that, okay, I'm studying a course on heat transfer like a 40 lectures. That has a well-structured plan, but research is not like that. Your tomorrow's plan depends upon what you get today. You may have a plan that today I will do this experiment, tomorrow I will do this simulation, but what if it doesn't happen what you are hoping will happen today? Then you have to rethink your plans. It's a game. Yes, it is a game. It has rules. It's like a chessboard. You're not thinking about today. You're thinking about what will my opponent do? What will I do in return? What will he do in return? What will I do in return? So you have to think. You have to have a foresight. It's a roller coaster ride. Of course, when you're at the top of the world, as I said, eureka moment, you have cracked the problem, you feel on the top of the world. But remember, what goes up also should come down. So you should be able to face the low period also. 6 months, 8 months go by. And remember the work we were talking about little while ago of Manendra. Many of you would not know that short paper underwent 6 revisions. It was not 1, 2, 3, 4 revisions. It underwent 6 revisions. And every time they chose a new referees because it was such a sort of groundbreaking work. So it's a pyramid. You build how do you build this room? You don't start with the roof. You start with the foundation. That foundation is built in the schools, IITs, Wikipedia, internet, TV. As you go up, so it's a pyramid. You go deeper and deeper rather than broader and broader. Some people think it's frustratingly slow and hard work. Yes, all of us have experienced that. And I'll show you a classical example of that. Some people think it's like a river, just meandering. I have no straight path. How does Ganga form in the beginning? There are a lot of small rivulets, then they form. So this is also, in the beginning, you may have a lot of ideas, which are very confusing, not very clear, but ultimately they form a coherent one stream. So it takes time. Some people think it's a Wild West with the cowboys and the guns. Yes, there are cowboys and guns in the science also, in research also. And I don't need to explain that, all of you know what I mean. So it's a journey. It has no fixed destination. Okay? So example of frustratingly and slow work, here. The manuscript submitted and the manuscript accepted. He's almost in his grave when he became the prince. So it can happen in science also. The recognition comes very, very late, but you should not be discouraged by that. Okay, so I think now we understand what the business is, that what as a researcher we are supposed to do. So maybe we can think of what could be the toolkit which we are looking for. And you should be able to ask a question. Identification, formulation, you should be curious. Any woman here wearing a blouse with the buttons? Yes, no? I'm not going to ask you to do anything. So, nobody? What side of your blouse buttons are on? Gents, can they tell? So ladies have on the left hand side. You should wonder why. It is just to distinguish between the two dresses for men and women? Or is just a manufacturing defect, or what is it? Yeah? Think about it. So that's the question to ask. You should be curious. You should have broad interest in several areas, making connections, developing analogies. Discrimination. Where to put your bets? You may have a lot of ideas. Which looks the most promising? This is where your knowledge comes in. Are you violating any laws? Conservation of mass, Newton's laws of motion, first law of thermodynamics, second law of thermodynamics. Is something inconsistent? Am I producing perpetual machine? You should be able to discriminate. This is your training. This is your education. This is your grades. Okay? Ability to iterate while learning from your mistakes. You are allowed to make mistakes, but not the same mistake again and again. Every time you can make a new mistake. You have a license for that. Okay? Most importantly, ability to think. All of these depend upon that you are able to think. All of you are capable of thinking. In fact, you are thinking right now what I'm going to say next. You are thinking that what I'm going to do after I finish my BTech, MTech, PhD, or what I'm going to have for dinner. This is all thinking. So what is thinking? Quickly, from students. Yeah, interpret something. Yeah. Something else? Okay. What is the basic biological purpose of thinking is to enable a living organism to survive by getting the things it needs and staying clear of dangerous things. Dogs do it, cats do it, birds do it, sparrows do it, we do it. Correct? When you feel hungry, where do you go? You want to get food. When you're not feeling well, you go to a doctor. When you don't understand something, you go to your guide, to your mentor. Irrespective of what one is thinking about, the underlying phenomena going on in your mind, in your brain, the biological thing is exactly the same. Exactly the same. You should read a book by an Indian doctor, V.S. Ramchandran, that how does your brain work. He has mounted several sensors just to see, and when he gives different stimuli, how does your brain work. Okay? For example, when you see something you don't see, you have not seen it before, what comes to your mind? You try to decode it. What would it be? So this period is filled with a lot of ideas. All kinds of ideas come to that what it is, what is going on here. Or how will you describe this picture? One line fact. Or this picture. This is how you think about things. I can tell you, when I give this talk to high school children, they are much more creative than you people are. Because you are worried about, oh, people will laugh at me. This is a stupid answer. Kids have no inhibitions. They say what comes to their minds. So, first thing about thinking is you put down all kinds of ideas, all kinds of thoughts which look relevant. Doesn't matter. Then you weed them out. If you don't have an idea, you have nothing to weed out. You have 100 ideas, you can weed out 80. So I also ask, what is the ratio? Let's say we have a circle inside we have a square inside a circle and a square outside a circle. What is the ratio of these two areas? All of you can do it. With due apologies to my colleagues, some of them may struggle to do it, but it's okay. But you will do it, you will use trigonometry, Pythagoras theorem. Answer is half. But let me tell you, let's think. Will your father be able to answer this question who doesn't understand trigonometry, or your grandfather? I'm sure he will be able to answer it, and much quicker than you will be able to answer it. So how will he do it? He doesn't know Pythagoras theorem. He doesn't know how to calculate areas. How will he do it? Well, this is what he will do. Rotate the inner square, and now what is there to be done? Each quadrant has an area exactly half, so the overall body should have exactly half. So this is the damage done by our school system. They teach you too much to think with the help of the equations only, so that you lose your native, innate intelligence. Correct? Okay. So there are 3 levels of thinking: instincts, learning, and understanding. Instincts you are born with. Baby doesn't get a feed until it cries, but baby is born with that ability to cry. It's not an acquired trait. The pediatrician does not leave the newly born baby till he or she has cried. So that's instinct. Learning is what you do from the school all the way to PhD, IITs, and on your own using internet, Wikipedia, books, your friends, peers, everybody. Understanding is when you combine your instincts and learning to deal with a new situation. I cannot teach you that. See, we can teach you fundamentals of heat transfer, mass transfer, separations, distillation. Your boss is not going to ask you, design a distillation column, we want to carry out this separation. He's going to tell you, we want to carry out this separation, tell me what is the best way. So now you have to weigh options. There may be several options. That's understanding. So let me give you 3 examples. This is a picture taken from an English newspaper, 1965. There was a coal-fired thermal power station, and you can see that on November 1st, 1965, these 3 cooling towers were blown away by the gale of 137 miles per hour, and each of these cooling towers is 375 feet, 125 meters. Such a calamity because there was no power for 2 months. So as something happens, you set up an inquiry that what went wrong so that we don't make the same mistake again. This is purely a chemical engineering problem, fluid mechanics problem. It's only a question of structural integrity that maybe these structures were not strong enough to withstand those winds. In fact, these structures were designed for 200 miles per hour. That day there were only 130 miles per hour. So that could not be a reason that it was not designed for that. Second thing, that could there be a hydrodynamic interaction between these 2 bodies? See, when winds blow, there are hydrodynamic forces, drag force. Could that make this collapse? So that time a very young man, chemical engineer, he visited us in Kanpur during the I case, Donald Gunn. He thought of a very simple model and he constructed, these are the cylinders, and he just varied the horizontal gap and the axial and the lateral gap, and he just measured the pressure drop, and he could see that there was a critical spacing, especially the horizontal, when the drag force on each tower could be 100 times more than an isolated tower. 100 times. Ultimately, the Royal Commission also found that the hydrodynamic interactions were not taken into account. This is making connections. This is, you can get a quick paper in Nature, a short. I mean, this is not a rocket science, but you just have to think. And he found that when the gap was just of the order of 1 diameter, and actually those towers had a gap of less than a diameter. So this effect would have been even much more severe. And second factor was because you see, if the air is coming from this side, part of the area is blocked by these towers. So the effective velocity impinging on the rear side of the towers is much more than the free stream velocity. So that was the main factor. And the second factor was, it was a high Reynolds number, turbulent flow 10 to the power 5. And even a small change in the direction of wind could change the forces on these towers. This is what we teach you in fluid mechanics course. Okay? So this is just making connections. Okay, my second example is, students probably would not know what is a fountain pen because they are used to smart iPad and all those things, and I mean, biros and all those things, but not. So, you know, goose feathers have been used almost for 3,000 years for writing. People write records, so take a feather, dip it in the ink, and just write on a paper. Now, what is the problem with that? It doesn't leave a uniform thing because you are dipping. Sometimes the ink just runs, sometimes there is no ink. So, it does not transmit ink evenly and smoothly onto a paper. It dries out, causes spots, causes poodles. So, you can't really write for a long time. You can write a short record. So how, when somebody is born, when was he born, where was he born, and all those things. You can't write a research paper. So let's say we want to now develop a device, which is really fountain pen. So what should be the product specification for that fountain pen? That's what we need to do, no? Then only we will know how to make it or what to make it. So ask yourself, what is the purpose of a pen? What would be an ideal pen? This is just like your brainstorming, just in your mind, that if your boss gives you that I want you to design a writing tool which should not have any of those disadvantages, how will you describe that product? That's problem identification, definition, formulation. Okay, so I would say I want to have a sufficient ink on the tip of the feather so that we can create a track of any length and there should be no residual ink on the tip to dry out or cause drops. Those were the disadvantages of goose feathers. I have just reversed it. Correct? That's what we want. So let's try to understand it. So we need ink only when writing, else it should not be there on the tip. That is, ink flows to the tip during its use, but otherwise there should be no room for storage near the tip. Yes, that's what we want. So, I mean, now you have half the problem solved, that I want that ink should flow to the tip when I want to write it. And when you write it, you press the pen against the paper. So that's your valve. That will open the valve somewhere so that ink will flow. But the moment I lift the pen off the paper, that valve is closed, ink is not flowing anymore. But when liquid flows down, the air has to flow up. So it's a two-phase flow problem. So now how do we achieve these two contradictory objectives? So this is how a pen looks like if you had a good look at it. It has a canal here. This is what you call a breathing hole for the air to go out. This is how, if I cut it, it looks like this. So I have a storage here. This is my fine capillary. When I press this, these two parts of the nib are drifted apart. A channel is created, ink flows. So tip of the pen consists of two parts. There is a fine canal along the pen to the point where it is connected to one. And when pen is not in use, canal is closed, so no ink flow is possible. As simple as that. Not a very difficult thing. But only thing is that when you hit upon an idea like this, don't go to Google or internet. Look for the answer. You have to put your feet on the table and think about it. If you go to Google, you will never think. Because your mind is now already conditioned. Google says this. So when the pen is pressed onto the paper, the two parts open up and ink flows into the canal and all that. It looks very simple here, and all these of course followed. But pen is actually quite a complicated machine. People paid up to 20,000 rupees for a Mont Blanc. Okay, so, but same idea. I mean, there is a breather, there is a slate, there is a tape. So this tells you that you build the level of complexity. You want to get more details, you remove, how do you peel an onion? Remove the outer skin first, then the next layer, then the next layer, then the next layer. So at each layer, you create more information, your problem becomes more defined. And this also connects to your, when I said some students define research as a river, because there are a lot of rivulets in the beginning, you have a lot of ideas, but finally it takes shape and you come to the product. Okay, now This is my sustainability business. I thought it will be appropriate to follow on from Rajneesh. This very pretty picture, it's a mall in Harare in Zimbabwe. It has about 6 floors, so much square meter area. It can park 450 cars, and the combined all floor area is 50,000 square meter. Why am I showing to this? Because you're not likely to go to Harare or to this mall. But this is a mall which has no air conditioning. It uses only 15% of the energy of conventional buildings of the same size in the same country. That is sustainability. I'm not hiding behind solar or tidal or anything. How did they do it? Okay, there is no mechanical heating, ventilation, air conditioning. Energy load is less than 10 to 25%. That 25% is only 2 weeks in a year. You know, the load on air conditioning depends upon what the outside conditions are. Hotter it is outside, more cooling we require. So this building is the inspiration. This is a termite, campus termite. This was the consultant design group based in UK who did the initial design. He was the architect. Okay. So what is campus termite? This is a mound of a termite, but the termite's home is under the ground. This is just an external structure. This could be 3 meters tall. And if you have a close look at it, you will see there are a lot of holes. You can see there is a lot of flow can take place. The temperature inside their underground nest, they are able to maintain 31 plus minus half a degree. You will require a very high-tech AC to maintain that precision, half a degree. Outside temperature can range from 3 to 42 degrees. This is a universal machine. I mean, so much variation in outside temperature, but inside they're able to maintain 31 plus half a degree. They're containing passages which link termite chambers or the bedrooms to the outside air. Termites farm their food, which is a fungus, in these chambers. So that fungus grows only in this temperature, 31 plus minus half a degree. When is the sun maximum? When it's falling just above your head. So it has a peak, area is 0. Maximum sunlight is captured by 0. All other times, sun is either falling from this side or falling from this side. You have a large surface area. So during the day, as the day passes, lot of sunshine falls on this. But this material has a high thermal capacity. It stores a lot of energy. It does not pass on the energy to the inside air. So air still remains cool. During the day, during the night, temperature drops. Now, part of this heat is lost to the surroundings, and whatever cooling has taken place, now there is a hot air inside the mound which rises because there is a cold air outside by natural convection. We may think of termites as very low creatures, but they are very smart. How do they control the flow rate? They line up against these passages. You close the areas, you regulate the areas, the flow rate changes. And you know when flow rate changes, how heat transfer changes, heat transfer coefficient changes. And all those things. So how did they do it? So this is all they have done. This is the idea they have used, that they have used a material of construction which has a very high thermal capacity, which gets heated during the day, but the inside air does not get heated to that extent. And as the sun goes down, the reverse process takes place. As simple as that. It only uses. So this CFD modeling was done by that engineering consultant group. They look at the flow patterns. So CFD study showed that there should be no direct sunlight on the walls. The north facade, on which the sun is very strong, window to wall area ratio should be only 25%. Balance between natural and artificial lighting. Windows to be sealed, they have to become light filters, controlling glare, noise, and security. So this is how it looks like. So now let me summarize for you. So this is how it looks like. So these are the passages. These are the chimneys. Air passages in the floor is going up and just going out. So you can see that it profiled in National Geographic magazine in May 2018, and it has been received several awards of sustainability, green buildings, and all those things. So what principles we have used? Sustainability, energy efficiency, green building, fins. If you look at it, they don't have a smooth structure. They have very prickly structure like cactus plant. How does cactus plant survive in a desert? Materials of construction with high thermal inertia, double thick brick walls, double layer concrete floors, transient conduction. It releases heat during the whole day and then in the reverse direction during the night. Minimize overheating by midday sun by minimizing the relevant surface area. It has a pointed top. Use chimneys to expel hot air, natural convection, no pumps required, no fans required. Then a Cambridge group got interested and they have done CFD modeling and some experiments using saline water as a source of flow. Initial tips provided by a group. This is sustainability. 10 to 15% energy consumption of traditional buildings. Okay. In real life settings, chemical engineering thinking can be a little more complex. So here is an example, chemical inputs. I'm using air for nitrogen. I need methane to produce hydrogen, ammonia, and all that. These are the parameters. So you should get into a system of systems thinking. What are your central ideas? Socio-environmental literacy. You're not working in isolation. Socio-environmental responsibility. I mean, be a good citizen. You are responsible. Don't solve your problem and create for somebody else. Collaborate, disciplinary practice, science practices. This is how you develop a holistic view of whatever you want to do. Yeah, so let me ask you a question. I'm not going to ask you how many elements are there in periodic table. Some 120, 123, right? All of you have a smart device in your pocket. How many elements are used to make that device? Take a guess, quickly. 10, 15, 20, 5, 10, what? Yeah, very good. 75, very close. Some for electronic properties, some for magnetic properties, some for sensing, some for optics, some for electronics, and all those things. This is how you think about this. So, different people have different styles of doing research. Some people like Linus Pauling, who was a Nobel laureate in chemistry, and the best way to have a good idea is to have a lot of ideas. And the best example I can think of is Wilhelm Ostwald, a German chemist who got a Nobel in 1909. If you read his biography, every morning he will come tell, Ashish, you do this, Vivek, you do this, somebody else, you do this. He'll come back after morning coffee. He'll say, no, don't do that. That was a stupid idea. Don't do it. So, I mean, that's one way that he was. But our Vivekananda used to think that take up one idea, make that one idea your life, think of it, dream of it, live on it, and everything. Use every muscle of your body to deal with that idea. And the best example I could think of was Gibbs, of Gibbs Free Energy. He was in that category. He didn't have a lot of ideas, but whatever idea he was, he just beaten it to death, Face rule has remained the same. I don't think there has been any need to modify it or change it or amend it. First and the last word. So this is part of your personality. I mean, people who are outward, very extrovert, they socialize with a lot of people, they are likely to have more ideas because they talk to different. All these elements in good measure are required to be a good researcher, but I also want to tell you that there is no substitute for hard work, no matter how smart you are. Even Einstein used to say that it's 10% inspiration, 90% perspiration. You have to sweat it out. And so I always show this graph. So there is a performance here and there is a stress level here. If you are in the green, you are really inactive, you are laid back, very little stress. If you are somewhere here, you are fatigued. And if you are over that side, you're not that productive, you have breakdown and all that. So you should try to be in this yellow region so that you're not killing yourself, but you're not underperforming either. So I had to apologize to all the faculty members here, myself included. We think we are doing a great job when we teach you, but actually that accounts only for 5%, sadly. So lecture is only 5%. 10% you do it by reading, 20% by audio visual, 30% by demos, 50% by discussion, 75% practice by doing, 90% when you are able to teach others. So I'm sorry, but we think we are doing a great job, but that's where we are, only 5%. Huh? Yeah, okay, so thank you. But even teaching part is, we can teach you that knowledge is knowing a tomato is a fruit, but wisdom is not putting it in a fruit salad. And he's one of my favorite authors who died. So the illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn. This is lifelong learning. Lifelong learning, and it applies to all of us. Okay? So you can see that I'm a little bit of fan. When I was a child, my mother said to me, if you become a soldier, you will be a general. If you become a monk, you will end up as a pope. Instead, I became a painter and I wound up as Picasso. So you should go where your heart takes you. There will be people giving you advice, unsolicited advice, some good, some bad. Listen to everybody, but in the end, I think it's your life. So you should live the way you want to live. And so, think more. Think with the help of physical and abstract models, exploit analogies, make connections. Group activities, open-ended questions, synthesis of multiple ideas, they foster your thinking. Staying alert, active, reading, solving puzzles, ask questions and maintain positive attitude. And most importantly, be away from the internet when you want to think. Switch off all your devices. Okay. So I think we have come to the end. I think I have mostly focused on this part, that it requires imagination, creativity, hard work, persistence, and thinking. Rest is, I think, all stuff. So thank you for your time.
Thank you, Professor Chhabra, for your profound talk. I'm sure many of you have questions. We have time for a few questions.
So thinking in engineering and science, like in engineering, there is no unique solution. There are many solutions. And in science, you have to be lucky to find the exact solution. So is there a distinction between these two?
Well, I don't make any distinction because science also has many solutions. Before, slowly we modify our opinion, we change our views, For example, Kepler, Copernicus thought a very different planetary system, but then Newton came along, he thought very differently. I think as more evidence becomes available, you modify your opinions also. We thought Newton's laws of motion were sort of fit for all, but until Einstein came along, he says, no, there are situations where they don't apply. So I think at the fundamental level, there is no difference in my view, I think. Yeah. I don't know whether that answers your question. Yeah, Raj.
How is the knowledge encoded in the environment?
I think the way babies know how to cry, exactly the same way. I think it's a surviving instinct. I mean, when I got interested in this, I'm just reading about them more and more. Yeah, but it's very, I mean, I was amazed. And that building came up in 95 or 96, so it's not a very old thing. I think one reason for Mike Pierce was that he was given a lot of constraints. He says, look, Zimbabwe is a poor country. We don't have electricity. So don't use a lot of glass. Don't use this fancy material of construction. That buildings look outside, but they are horrible to be inside. So I think, and then together with the engineering company, and now by the way, there is 3 buildings in the UK. Their Internal Revenue Service, and there is a municipal corporation office, and the third building I don't know, which have followed this, and they are using, they call them naturally breathing buildings. Yeah, so if you just look up, there are articles in New Scientist. That was the Zimbabwe building was described in Zimbabwe Review, a very obscure journal. So I had to spend some money to get that 3 pages. It was available only in the British Library and nowhere else in the world. Even Zimbabwe didn't have it. So I think, I'm sure. I mean, we just still learning. I think all I'm saying is that the nature is the best designer, perhaps. I mean, our buildings last 100 years, but buildings made naturally are there for 1,000 years and all those things, I think. So, yeah.
Philosophical question. How do you basically differentiate between imagination and thinking? I mean, I typically tell students, don't keep imagining. I never tell them, I don't tell them to keep thinking. Maybe I need to change. I'm just trying to get your opinion. I always tell them that imagine. But is there a difference between, am I saying something wrong, or there is more to it for thinking rather than
I think I am more than you are in this matter, because this is a very philosophical question. But I can go back and ask my sociologist friend and psychologist. But I mean, one thing I want to say that moving to a complete university has been a very, very life-changing experience for me, because my entire working life was in monoliths, only primarily engineering, in IIT Ropar also, here also. But now we have departments you cannot even imagine, international relations and governance studies, and the type of things they talk about, and then in addition to psychologists, sociologists, and the type of speakers we get, it's just a whole different world. So now I go to their seminars, and every time I ask, they say the basic skill needed at the school level, college level, every level is the critical thinking. And they say, yet it is the most difficult skill to teach also. It cannot be taught. We can only facilitate, because different people have different styles of learning, different styles of thinking. So, but on the other hand, our focus is on making uniform, structural, modular, whereas thinking is very, very slow process. And in fact, only last week I discovered a letter written to the Nature by Professor Tate from the University of Edinburgh. He says, cramming in the universities is becoming a problem. And this is in the 1890s, because it's published in Nature's first volume 10 or something. So his suggestion was that how students should be given an exam, that after the semester is over, they should be sent away to seashore with no pen, no paper, nothing. They should lie fallow, assimilate what they have learned, and then they should come back after 6 months and take the exam. So when I told this to my friends in psychology, they said this will be a disaster, the whole class will fail. Because 6 months they would have forgotten what they have learned. So it just won't work. So, people are concerned about these things also. Only thing is that I think education is all about slow, it's inherently a slow process, whereas we are trying to fast track everything. So it's really very, very counter to the basic tenet of education, I think. Yeah. So I think I'll just stop here. Sorry? Well, there have been experiments done in this institution itself. Maybe they're not doable today, which at least gave a lot of freedom to faculty to do all kinds of things. But I think now we're becoming more and more structured and standardized. Yeah.
Thank you, sir. Now I invite Professor Jayanki Singh to present a memento to Professor Raj Chhabra.
I can come down. No? You can climb.
Chhabra is saying I'm younger than you.
Which is.